is just a new toy that I came across this week. Somebody sent me a link for, you may have seen it. Basically just a souped up servo motor. Like the sort of things that are in that Fidget kit, but there's about 2 or 3 of them inside it. I'll put the link to if anybody's interested in it or programming with it there. I think he has a little bit of software associated with it. The links up on just there on Moodle about that robotic figure add-on. Somebody's presenting it as a paper at some conference, I think, or IEEE German. Anyway, welcome to the third lecture. We're going to have a look today at nodes and some of the hardware and give you, hopefully as normal, a little intro with some demos of things that we work with either in labs or with sort of project students and the like. We haven't got one of those fingers just as yet. One of the things that we do work with is this little kit by a company called Makey Makey. You may well come across these on open days to it. Got a circuit board that picks up touch and turns that touch into a key press. So it makes a sort of key press out of it. Again, I'll just sort of pass them around just to have a look at what the board is. These are just USB powered again. And you can get it to pick up the touch of almost sort of anything, really. And just to, there's some more demos just coming up, but I'll just sort of show you a quick demo here. That's like just, this is GarageBand, a sort of Mac piece of software. Just allows you to do musical typing by pressing the keys to get a key press to turn into music. But using this Makey Makey board, we can link it up to things like Icons of Fruit. Or 2 together. Needs to make a good connection, so I'm just keeping it. So you can join any of them together. And it's just, we have this on open days, it's just a bit of an attention grabber. It just completes a circuit, basically. You'll see on the board as it's coming round, there's the different letters of a keyboard and the up and down arrow keys, that sort of stuff. And when you touch something, it just completes a circuit, and so long as it can conduct electricity, which anything with the water content can, it can sort of pass it round. But they often offer these out for little sort of demos. It's called, as I say, this little Makey Makey thing. We've got a all of these are just making a circuit, and then that's linked into driving something.
Hi, I'm Jay.
And I'm Eric. We're graduate students at MIT Media Lab.
We have a dream that everyone is an inventor.
So we created Makey Makey to let you invent just by alligator clip. Alligator clip stuff like bananas to your Makey Makey. When you touch the banana, your computer just thinks you're touching the keyboard. The front has arrow keys, spacebar, and mouse left click. When you're ready for more, flip the Makey Makey over and you've got more keyboard keys and support for the mouse. No programming, no breadboarding. You don't even have to install software. Just plug it in with USB.
Order your Makey Makey today and start changing how the world works.
That's the promo video for them if you like. But it's really just another sensor board for picking it up. What you connect it to depends on yourself. That board itself just generates a key press, and then you can do whatever you want with the key press. So if the ZX, ZC and V are sort of left and right for controlling a game or something like that, or you can pick up the mouse clicks. You can just replace a keyboard and mouse with whatever you like. You can replace it with fruit if you want, or anything that conducts, as I say, sort of electricity. So you get people making things out of Play-Doh and that sort of stuff. You can link it up. We've got a quick demo here where inside the box, I'll just have to open it gently because there's other kits inside the box. Inside the lid, there's one of those motors that you use in the labs. And I've got a quick piece of software here. You can bring it up. Which detects a quick bit of software which detects the key press and then just moves the servo to a particular position. So when running this one, start it running. It's waiting for a key press. If I do a normal key press, that's okay, but I can again sort of do a key press on here and fingers crossed. It moves the motor accordingly to moves the servo motor to a particular position. So you might sort of get some game sort of thing built out of this. I haven't plugged them into the actual fruits that it's supposed to be going to. That's just a matter of configuration of which ones you sort of get it to. But those sensors and actuators that you're playing with can just be linked to other ones, and vice versa. You can take those sensors and connect them to something remote. That's what we're doing in the labs this week. The ones who had their lab yesterday, we were doing this bit on MQTT, which is a way of getting the data from one place to another one, and out to multiple people perhaps. So we could have some sensor picking up the data and broadcasting it out, and in this case a motor picking it up to turn to that particular position. It could be turning other things on. That's that sort of idea. There's another little demo just about. I'll just sort of bring it up on the. This is something by a company called Flick. Started off as a Kickstarter application a couple of sort of years ago. It's actually just a small, rather like those Amazon ones. Just a little rubberized button, takes a click, double click or a long click to work with, and I'll sort of pass that round. You can put these anywhere you like. It's rather like that Amazon dash button that I showed last week. That sends off a signal, and we'll show how that signal can be relayed out to other sort of items. In my case, I might have it sort of a link to, say, a music player. No, just need to a few of these demos work together. I've got my phone connected just through a speaker. I have to turn the VGA on to get the speaker. But I'll just show you the front of the phone and we know what's going on there. There's the phone. I'm about to play some sort of album track, whatever, you know, the usual thing with a sort of play on it. Noticing the play thing, if I double click the button, it says, well, black. It's playing, but my speaker's not connected. If I just turn the VGA on where the speaker is, So controlling the phone, if I do a double click again, turns it off and on. So it's just a remote control basically for the thing. Now that's just programmed the double click part to it. Just sort of turn it off. I've got a single click program to send a mail message. So if I just do one click, you'll have to believe me that it sent a mail message, but I know you won't, or you shouldn't do. If I go to my mail thing somewhere, get the right thing, whichever one it is. There it is, you need to sign on, all that. Top email there, just received. If I do another single click, one gets sent. Might take it a couple of sort of seconds just to get through. I'll click that top one. I hope my phone does. I'll just click that first one. And there's the, yeah, you've received a test mail from this black flick MMU button. Again, sort of do it one more time. I'm just hoping that some of those will sort of come through in time. It all depends on the email server basically there, for it, so it's how fast it comes through. So there's quite a few ways you can work in with this particular one. I'll show you again a bit of sort of how we program it. Flip back to the dock, Cam. This flip button and MMU, you can program the click button, a single click, in that case sending that Gmail, a double click, navigating to the player. The long click, I'll pass it around just for sort of playing with it in a moment. The long player, well, I'll just sort of, you can sort of program it, it's come to its own little suggestions to sort of work with. So you can get it to connect to, say, Hue lights at home as a Philips Hue or different other sort of home ones. Perhaps do some sort of phone control if you want. Maybe sort of let's try and toggle in the flashlight on. So a long one should hopefully, if I hold it in long, turn to light. It's a bit hard to see maybe, sort of, or a long one toggles it off again. So that was that easy to program. That particular piece of software comes with a little sort of interface to be able to sort of do that programming. I'll send this round just to have a look at, see what these sort of feel like. They've got a tiny, the usual sort of watch battery communicating within it. What we'll do in the lecture session, we'll go over how these sorts of things communicate and how they're sort of passed around. I'll start the register going round as well. So just, as I say, just a few quick sort of demos on what's sort of been happening with those. Now, I'm going to say, as it goes around the around the thing, people will be test clicking it. You're sending an email, turning the sound, you're turning the music on and off. I've not got the VGA on, sort of plugged in, so you won't necessarily hear it. I did used to have a few sort of surprises built into it, like a fart generator or something like that generated you were going around, but that all got a bit too childish in the end to sort of work. But they're all just instances of something that's gathering something out of your environment, some sort of sensor, either a click or a touch in the sort of fruit case there. Keyboard presses, all those sorts of things, and then they need to get it out to somewhere else. They need to take that sensor and send it to some receiver that's going to do something with it, play a sound, start the music going, turn the motor, open the door, those sorts of things. as I say, that's what we're just going to be having a look at today. This phone's buzzing away to see all people are sort of trying, running it. We're going to have a look at how to link these sorts of things together. Just get my little clicker. So we're on to lecture 3, which is all about the hardware side of things. The sensors that are connected, and more importantly later on, the nodes. Sensors and actuators, that's just a bit of sort of info going on in the background. The real sort of important parts today is going to be this node architecture. That's the mail message that people are sending. There'll be a few of those arrive by the end of the day. So the key part of today is going to be this node architecture for it, with the sensors dotted out, either fixed in a room, like a swipe card as you come in. That swipe card idea, by the way, you've probably got enough to start programming one of those now, because you know how to pick up an RFID card, and you know how to send that that type, and hopefully it's a reader ID, off to some server somewhere. And all you need at the other side is a database to start storing those sorts of things in with the time. You've got like a registration system built. We'll be doing the database next week for this. But basically, these sorts of nodes are either going to be commercially evolved nodes that can collect the data and broadcast it out, or it's going to be something that you build yourself. And in the labs we're building them ourselves, you've got a series of sensors. In that case, connected to, say, a Raspberry Pi or something. You've got them connected to your laptop, to your desktop or something like that. And together, that computer, the sensor nodes, and something to do with communication. In this case, it's got that XB communication part to it. That can send it out using a protocol called Zigbee. That then becomes so it can communicate with another node somewhere else. Or perhaps a gateway. It might be connecting through to your router, or just some centralised system in your house that's connected to all these other nodes. We've not really been using the Raspberry Pis. It would just take us too long in labs to be able to get Raspberry Pis and all these other nodes connected together. One or two people have been asking me, where can I get these sensor kits from? Sorry, I'll just turn that volume down. Where can they get hold of these sensor kits? You can buy the fidget sensor kits, but they're really overpriced for what they are. We only get them because they're robust and they're easy to work. You just sort of plug in the USB. If you're wanting to try stuff at home, you couldn't go worse than really getting sort of the Raspberry Pi approach with things like Arduino boards to plug into it with all these sort of cheap sensors. A lot cheaper, just a bit fiddlier. It involves actually putting them into breadboards and perhaps even a bit of soldering to fix them in there. And it's something that we can't really do in the labs. We're essentially concerned with software writing in that rather than hardware building. So we've concerned ourselves with taking existing sensors that we can just plug in, or commercial sensors to work with. But it's the same sort of basic idea. You'll just have some centralised part with the sensors connecting out generally to some sort of node that can get out on the internet and broadcast it through. So we've got those different types of sensors, whether or not they're sort of omnidirectional sensors like a microphone, things that detect by broadcasting out a beam like a motion detector or a distance detector that sends out a little sonar or light beam to detect how long it takes to get there. Active sensors as well, working in similar sort of ways. They all come back with some sort of reading, typically in some sort of units to sort of pick up on. Now the hardware manufacturer will build into that sensor board, or that little slider, or the force button, some sort of what we call a transfer function. that will take that electrical signal that they've got, because what's coming in is something like, as I say, like radio waves coming in, it's detecting heat, it's detecting sound, detecting some sort of movement. It's got to take that physical representation and turn it into an electrical signal to send out for it. That's done using a transform function that's generally built on the board itself. It's not something that you have to do. The manufacturer will supply you with a sensor that will send you back a signal according to what it's detected in the outside world. It might be a straightforward linear function like A plus Bx, which is a sort of straight line. It might be a sort of curved one, to get it, where basically when a particular signal comes in, it generates a certain voltage. Now that's what you're picking up in your Fidget sensors. When you've got that sensor kit board, and you could either get the voltage, and it was something ranging between 0 and 5 volts, I think, or you could get that the voltage ratio, which scaled it to 0 to 1 to sort of work with. We were just picking up on whatever the manufacturer gives us, and we have to interpret that then in some way. It may be that you can get an inverse transfer, saying, well, if I want this value, what does the heat have to be to get into it, or what does the distance have to be to sort of work with? And as I say, it might be linear, it might be non-linear to work with. It may be that you've got like a polynomial function or multiple values coming in, like humidity, you've got relative humidity and temperature going in. There may be a saturation point at some point. Now, as I say, that's not something that we as software designers really sort of bother with. If you're an engineer and you were building these sensors, then yeah, you'd be sort of looking at these sorts of transfer functions to decide what voltage to send out. But it's just sort of to fill in really a bit of the background about what's sort of happening within it. But these functions that they're sending out, to us, it does matter, those values that we're receiving. Things like the resolution of it, and the accuracy and the precision, they tell us a bit about what you're actually measuring. I could say, just as an example of resolution, I could say from here to that wall is 0 kilometres to the nearest kilometre. Well, yeah, that's true. It's not very useful though. I might say 20 metres to the nearest metre. Now that resolution there is, I'm giving a metre resolution. And, you know, I'm not saying it's, I'm saying it's like 20 metres at a rough guess. I'm not saying it's 20.63 metres, but I'm going to the nearest metre there. My resolution is to the nearest metre. Now that's okay, perhaps measuring to the wall. If you're talking about something approaching, say, an RFID pickup, a metre resolution is not very good for that. You need something a bit sort of smaller. So the sensors you buy describe that increment of stimulus. How big a change does it have to be? How accurate is it? Is it accurate if I measure from here to the wall to the nearest metre, to the nearest centimetre, millimetre? And the more accurate you are, generally, the more it costs. So if you're prepared to put up with just sort of very rough values, say to the nearest centimetre to that wall, you'll get a really cheap sensor to do that sort of thing. If you want something that's to the nearest millimetre or micrometre, you know, sort of like a millionth metre, then it's going to cost you a bit more, obviously. And the same sort of things with temperature values or humidity values. They've all got certain increments that they're going to sort of be working in, and you just buy the one that fits your particular situation. So when you're going out sort of buying these sensors, you have a look at what their resolution is and what that sort of accuracy is as well. And is it repeatable? If I measure from here to the wall and then do it again, do I get the same value coming back out of it? Can I repeat that request over and over again? These next few slides are a bit just sort of filling in a few of the blanks of the different types of sensors, about whether or not they're dependent on some sort of, say, capacity value or resistive value. Resistive value, yeah, a change in resistance in the environment. So you might have force and heat and magnetic fields sort of falling within that. So there's a range of different sort of types of sensors that you get. Magnetic sensors, detecting sort of magnetic fields, if you like. That can help tell you where you are on the Earth for it. Now, a range of these are often just built into phones. But we can also get them these individual sensors. Again, it depends on what you're wanting to pick up. Thermoelectric for generating voltage out of temperatures. Pyroelectric for sort of generated when something's heated or cooled. Sound levels. A range of these sorts of things. Now, fidgets do their own stuff. When you just go to their sites, you'll see all the different sensors that they've got there. And your kit just comes with a small selection of them. They do hundreds of these sort of sensors to work with. And you only need to go to something like Amazon and do a search for sensors there, and you get the really sort of cheap ones to sort of work with. Some might be more specialised pH meters for acidity, carbon monoxide detectors. Again, it just sort of depends on what sort of thing you're after. But a lot of these are already built into smartphones already. They've already got gyroscopes, fingerprint IDs, sort of with a light sensor, they can sort of do distance measurement for it. A whole sort of range of those built into it. So if you've got most people have those things, you'll have a smartphone that's got a range of those already, and you can, either the Android or the iPhone APIs will be able to pick up those sensor values to work with. Outside of that, you're down to building your own sort of ones. On the other side, you've got the actuators, the things that actually move, like a motor, a servo motor going from one position to another. They may be electric, they might be pneumatic, working off sort of gas-powered or hydraulic-powered ones. To it, mechanical ones that turn like a sort of big cogs turning one thing to turn another one. Actuators that either spin round or move in and out, linear actuators, all sorts of things. It might just be light, might be turning something on to warm it up. You can also have things like relays connected. And a relay just allows you to take the tiny voltage output by, say, your Pi or your PC, that little 5-volt thing in the small wires. And on the other side, you can connect something like a 240-volt wire, like a big thick wire. Because if you try to pass too heavy a voltage down the thin wires, you'll just melt the wire. And you'll destroy what's behind it. Whereas a relay just allows you to do a switch. It allows you to say, look, when this small switch clicks over, make the big switch click over as well. So you could effectively do things like turn kettles on, or turn some other electrical goods on. We don't do that in our labs. We don't really work with the relays in our labs. We'd have to health and safety up our labs, basically. We started letting you play about with sort of 240 volts and the like. Then we'd have to have the labs kitted out like the engineering labs and things. And again, it's really going a bit sort of off course of what we're trying to do here with the software one. Now the signals coming out. You're seeing some of these sometimes, even when some people in the lab yesterday were moving the sliders and broadcasting out the signal, and even when you weren't touching it, it seems to be trying to send a signal, because they're really sensitive, some of these. And there's cases where the digital signals going out, or that you're picking up, could cause a bit of a problem with sort of noise. To it now. Whether or not this will pick up or not, I don't know. There was a case where a series of sensors to detect the northern lights, they sort of detected EM radiation in the atmosphere and would trigger off things like cameras or alerts to people to say, look out your window now, the northern lights are coming. And these sensors were triggered off by a lawnmower, basically, lawnmower sort of activity. You may have seen this on, if you've ever heard your car alarm going off, and it's because a motorbike's gone by. You have these motorbikes with unsuppressed ignition systems on them. and they send out, as they're going along, they're broadcasting out an electrical field, and that can often set off car alarms. And it's a similar thing going on there, basically. So the signals being sent out can be really quite sensitive to work with. And what you may have to do is just suppress the amount of noise that you're getting in some way. Either by suppressing the rate at which you get it, or perhaps by smoothing it out, some data smoothing. Anybody who's done a bit of statistics might have done something called linear smoothing and exponential smoothing, where if you've got, maybe sort of draw this out. No board in here, so. Where if you've got a range of values coming in, you may have your values sort of jumping all over the place, or still jumping all over the place. Oh, sorry, screwing that on there. Technology working. So you might be detecting values coming in. Now, you as an intelligent person can probably recognise a trend going through there. And say, okay, although it's spiking up and down those values, there is a sort of trend either for this bottom one, where it seems to really just be like a not very well drawn straight line, or this one's perhaps going up. And you've sort of got a curve going through it. And by using these sort of graphs, you can then use it to be able to predict what's coming up, or fill in missing values, that sort of thing. So the jagged bits is just that raw data coming in, and you're trying to apply some sort of smoothing onto it, either to get a straight line, or perhaps a sort of a curved line, like a polynomial, to sort of work with. Now, there's various techniques that can allow you to do that. And again, it's a bit outside the scope of what we're going to be doing in the labs. But if you've got some sort of project involving sensors, you probably at some point want to do some sort of smoothing where you take successive values and you sort of almost like get an average of the two. You take X at position 1, X at position 2, X at position 3. You vary that I going from 1 to however many values you've got to provide some sort of moving average. Now that might be initially sort of a bit frightening for people who aren't, who don't particularly get on well with sort of maths, if you like. But basically, finding an average of a few values. You say, look, for the 5 values either side, I might take a central value and pick 5 values this side and 5 values the other side, and I'll take the average of all those to mean, well, that's really what it should be. And that'll take into account the noise that might be, the more values you take perhaps, the smoother that might be. So you can take, say, 7 values there, halfway down, take a list of 7 values and just take the average of those to calculate where it should be. There's a range of these to sort of work with, and yeah, I don't want to get too much into the statistics behind it. But the general idea is you will apply some sort of moving average, some smoothing routine to work with on these. Now the sensors that we've been working with so far we've built our own. You've got this PC on your desk or your laptop, you've plugged in some fidget sensors to it, you've plugged in an actuator to it, and you've made your own node architecture effectively. Now you can do that, but you know hopefully that you can't really sort of deploy that. You've really only got a conceptual model. You're not going to take that laptop with these sensors connected and mount it on the wall here or something like that. Yeah, you could imitate this thing by having the card reader. You could sort of do that just by having your RFID reader in your cards and plug it into your laptop, and we'll stick the laptop on the wall and put the card next to it. Probably better if you could have a sort of made up one, really. That's you're getting into product design then, where somebody's going to take that conceptual model and build it. You can have specific ones, like that sort of card reader, or you might have more generic ones to build up one of these, what we call a node. And here's just one example, a sort of commercial one, to give you an idea of the size there for it to sort of work with and its capabilities. We call an object a thing, if you like, a node, if it's got those capabilities. If it can do some sort of sensing in its environment and or actuating, if it has got some sort of microprocessor to work with, if it's got some sort of communication capability to be able to send that data out somewhere else, and it's got a power supply. And a PC has got all the last three anyway. It's got, your PC's got a microprocessor, it's got Ethernet or Bluetooth built into it, it's got a power supply, whether it's a battery or electrical cable built into it. But if you're going to shrink it down into something like one of these, they're the sorts of things that you're going to need into it. They're all going to need a power supply somehow. This one probably wired into the wall. They may work off battery. It does need to communicate. This will need to be broadcasting out that type that it's read out to some sort of centralised server. So you've got to have something to communicate through. The thing that's most common with these is that the power supply, we generally have it as being powered by battery for Internet of Things devices. If they've got a power supply, it means that they're really limited in where they go. You've got to have either a wire coming out of the wall or a socket available to sort of plug it in. And often we really wanted to deploy these on the sides of buildings or out in the wild somewhere, that sort of thing. And it's usually the battery that's the main design issue of these nodes. And until we get some sort of breakthrough or revolution in battery design, sort of like things like instant charging. You can get instant charging in 2 seconds or something like that, rather than having to wait an hour for it to sort of charge up. Or better solar power to sort of work with, or something that doesn't sort of work on that. But in general, you're limited by the battery, because that drives the communications, it drives the microprocessor, the sensors sort of work with it in this sort of diagrammatic form here. And it's that power supply that's going to limit you. The communications you've got, and we'll look at these next week, that will vary according to what type of node you've got. Because you've got a wide range of wireless communications like Wi-Fi and Bluetooth. We'll have a look at Zigbee, and this Z-Wave, various ones like this. They've all got different power requirements. And hopefully you probably know already that things like Wi-Fi are really power hungry. If you leave your Wi-Fi connected all day, most people's batteries now don't last a day. Well, that's why all these power supplies are the little top-up packs that you buy. People go in with a spare battery for them. Or you sort of you take it off your charger in the morning, and you either need to keep charging it in the day, or when you get home it's back down to 20% and you have to sort of plug it in to it. That's because your phones is really just like a big node, and it's communicating all the time. There's ways of cutting down your power consumption, to turn off your Bluetooth, to turn off your Wi-Fi, because it's those sorts of things that are typically using all the battery power up. But that's the sort of components that a node would have. And either you're going to build your own, or you're going to get a commercial generic node. This is just a sample one, as I say. This has got certain specifications we're going to have a look over and what sensors it's got in. But one of the key things that will come out of this is why these things can be so cheap for it. But certainly if you want to use things like your laptop to power these, well, laptop's going to be 300 quid at least to buy. You're powering it by a Mac, sort of one of the bigger laptops or something, you're getting up to almost 2,000 or something, depending on what's in it. You can't have that, that's just too big a thing for driving these. Now these little sensor boxes are typically made using old technology. To give you an idea of what's in there, but the processor, for example, there is an old 16-bit architecture. For it, nobody uses 16-bit processors now. When you download software, you ask, do you want it 32-bit or 64-bit? And every laptop's now 64-bit to sort of work with. So these are really using really old processors to use, are really cheap to manufacture. And the reason why they can use these is that they're not driving things like Windows 10. They're not driving Linux or these, the Mac OS X and things like that. They're not playing big media files. They're not driving these big colour screens and the like. So there's no need for a lot of high processing. And even the memory there, you can see that, that thing's got 1 megabyte of external memory, and internally it's talking about 8K and 116K memory. Tiny, really sort of minute compared to that diagram that I put up last week about what's a typical phone got in now. When you get a phone and it's got at least a gigabyte or 8 gigabytes of memory plugged in it, the processor speed is whatever it is. That's really just to drive your applications that you've got. There it's got a few sort of interfaces. This particular one has got a USB interface to it. It's got a few sensors attached, a couple of light sensors, and it's the capabilities of the light sensors, where it sort of peaks for its sensitivity of light. This temperature range that it can detect. Sensor there ranging from -40 to 120 degrees C. So fine for generally anywhere on Earth, but not really fine for using inside an iron smelter or something where it's sort of absolute zero values. But you've got an idea there of the resolution and the accuracy of that. That resolution, it goes up in 0.01 of a degree to get to it. And it's accurate to half a degree. So although it's saying you've got 32.01 degrees C, it's plus or minus 0.4 of that for its actual sort of accuracy to work with. And similar things there for the humidity. So that thing's tucked away just inside that box, really for it, and programmable, so you can put your own software on it. It's got a power supply. Get up to the power somewhere. Well, communications part to it there. How fast can it communicate? What's its range there? 120 metres outdoor. If you attach an aerial onto it, you'll get a bit sort of further. Indoor, 20 to 30. So sort of Bluetooth-ish, I'd say there. An idea for how much current it draws. So this is going to be important to sort of know the spec of. What does it draw when it's actually working, when it's transmitting data, and what about when it's just sleeping, when it's just ticking over, doing nothing? Like currently, you're drawing very little current for it. You're all sort of laid back, just having your, okay, he's talking at me, I'm sort of doing nothing. You're not really drawing any energy. As soon as you start talking, as soon as you start working or moving about, then you start drawing your energy, and that's when you start using your breakfast and all that. So for there, that current draw says it's drawing 1 microamp. I think that's per hour or something, as opposed to when it's receiving RX and TX for transmitting, it uses almost 20, well, more than 20 times as much, sort of thousands. Get the thing right for that. A milliamp and a microamp, one's 1,000 times bigger than the other. So it's using about 18,000 times the amount of power to transmit and receive data for it. So when it's actually talking or listening, it's really using a lot of power, as opposed to when you're lying asleep in bed and you're not using any power sort of coming through. Your power consumption goes sort of right up. So you probably want, in these things, to cut down on the amount of transmission and receiving that you're doing. To not be broadcasting all the time, because otherwise you're really going to go through your sort of power. Because a power supply is just this 2.1 to 3.6 volts, really it's like a 3-volt battery put in. You get 2 AA batteries, 1.5 volts each, so got 3 volts of it there. It uses either this primary AA battery for running it, and then a rechargeable one. And again, that sort of tells you how long this milliamp hours, how long these things can sort of run for. And you can sort of work out from the previous one. That's how if that's using 19 milliamps per hour to transmit, and you've got so many milliamp hours, you can sort of work out how long that battery's going to last, if it's going to be sort of transmitting all the time to sort of work with. So the battery capacity there depends on how much it's using. If you get, say, CPU operation of about an hour a day or so, then it'll last about 6 months, this particular one. If it's sort of doing much more transmission, then obviously it's going to sort of use more. The reason for knowing this is if you're planting these sensors out around your own universe, inside your own environment, so some of these run on the top of buildings, in trees, forests or whatever, out in remote places, you want to know how often you need to go back and change that battery. So are you going to be going back every week, every month, every year to sort of get to it? It might be useful that it could tell you that the battery's running down in it. So we're building together, just looking back, that's a sort of, I'll say, a sort of commercial one. But that's the sort of generic idea of one of these nodes. That they've all got these sorts of things in. You've built that sort of thing in the lab, where the node consists of your PC connected to these sorts of things. Or it may be that the node's even just down to that little button that's gone round. That little button is a node in its own right. It's got a sensor, that little click to it, that's detecting one double click or a long click. It's got a power supply battery, the little watch battery. It's got some communication that's Bluetooth, to be able to communicate with the centralised node. So that little button, as I say, gone round, is really just another one of these nodes to work with. It's a specific node, whereas these sorts of things are generic. So it depends on the situation that you're dealing with. Final point really here is just this bit about, if we've got all these nodes together, you've got some nodes that can't really transmit too far, like that little button going round. That can only, it's a Bluetooth based one, so it's only going to be able to send it 20 or 30 metres. And that's going to be no good if if somebody's clicking that button and the receiver's a mile away or something like that. So what we might have to build is a network where these messages can be passed through and have some sort of communication architecture so that eventually you can get to some gateway node that's a powered one that can then broadcast it out to the internet. Well, certainly that little button isn't Wi-Fi connected. That's not getting a network connection. It was going through my phone to sort of get that. The phone now with the gateway. And you might be, it's a case of having to get to that centralised one, whether it's some sort of mesh network like this sort of one is, or what we call a star one as well. So you've got these things at the top, they're your nodes, and they somehow need to get to a gateway. And the gateway is the thing that connects to the, as I say, just to the outside world. It might be a specialised hub that comes with a kit, like Philips Hue. You've got your those light bulbs. Each one of those is an individual node, but it comes with a centralised hub that it connects to. That is actually then wired into your local router for that. It could be that the software is just on your PC or your phone. That button, they were going through the phone, and that provided the sort of gateway out there. And once you get onto the internet, you can then start storing that in a server. Now, in terms of what we've got in the lab, we've got that top part. You've got your things, your network to connect through to. It might be the RFID connecting. It might just be a wired connection, just a USB plug. The gateway is your PC itself in that case. And you were then, last week, you were then sending from that gateway out to the server over your sort of internet to doing it. And this week we're having a look at that MQTT as an alternative way of sending that out. There's a few just references here just on if people want a bit of sort of background on what sort of standards are being used here and data rates. We're going to have a look at these a bit more next week when we look at the networking part of these. This is just sort of like an overview of the sorts of ways of connecting them, either in a star type network, where each node connects to that centralized one, or in a mesh one, where potentially the nodes can talk to each other and pass messages on to get to it. We're going to be trying both of these out in the lab for you to sort of decide which one is the best technology for it. Finally, some might be beacons, in that if they're able to broadcast and listen, they can both sort of take in sensor information but also sort of broadcast it out. You might have ones that are more got a better power supply, if you like, inside it, and can broadcast out using a better network protocol. So some of the small ones might just use things like Zigbee or low-powered ones, and then they can talk to another one more like a beacon that can then send it out a bit louder, a bit like somebody with a bigger voice, if you like, and everybody's whispering to him, and you'll be able to shout that out. And again, we'll have a look at some of these in a bit more detail. I don't want to get into too much of the network protocols, the sorts of things. If you've done the network and operating system modules, you'll have done all that to death. But I don't want to presume that everybody's done the network and operating system sort of module. So we'll cover it with a light touch, really. Next week we'll be having a look at these, how the networks work and how the operating systems, not necessarily how they work, but what type of operating system you can use with these. But we'll leave it there for this week. We're just gone to the 10-2. If you can bring any of the sensors down, anybody who's still got one. And also if you can bring down the register, because I know one or two people may not have signed it. I'll try and put it here at the front. Sorry?
Got the register by chance.
It should be coming down. It went around the paper one somewhere, so I'm hoping somebody will just bring it down now.
Oh, cheers. Always. £9 the kind of thing. Honestly, about right class. What's your register? Yeah, there was.
Somebody brought the register down. There's a paper register somewhere.
Yeah, probably level person.
Somebody left the paper register just on the desk. Can you sort of see it anywhere?
I've all signed it.
It's okay, you can superimpose the map dimensions and just like that going and sort of it's really like we have to go further for the next one. And the first one's the last one. But then you sort of break it down, you sort of merge this time. So yeah, that's